Welcome to a video on the chemistry of Group 1 metals, suitable for use with IGCSE chemistry. I haven't made one of these videos for ages, so you'll have to excuse me if I sound a little bit more enthusiastic than usual, and probably the quality of the video in terms of the editing and the writing will probably be a bit worse than usual. So let's get started. Group 1 metals, often called the alkali metals, and unsurprisingly, here they are. In the periodic table, this is Group 1, and they're in Group 1 because they have one electron in their outer shell. So we're going to look at lithium, sodium and potassium predominantly, and they all react in a similar fashion. And the reason for that is because they all have one electron in their outer shell. And for metals, they have, some might say, surprising physical properties. If you get a sample of lithium or sodium or potassium, I have to say I'm not enjoying the pointer. I'm going back to the sort of dot. Let's see if that works. Much better. So if you get some lithium or sodium or potassium, they're surprisingly easy to cut. They're quite soft. Which you wouldn't expect from a metal. Even someone with my pathetic physical strength can actually cut samples of these metals. So they're quite soft, and relative for metals, they also have low melting points relative to other metals. And the reason for this is that the metallic bonding is actually quite weak within these metals. And that's because you've got, metallic bonding is the attraction between a metal cation and the sea of delocalized electrons. Now, as the metal cation in Group 1 elements only has a 1+ charge, therefore it doesn't attract the delocalized electrons as strongly as perhaps metals in Group 2, because their cation would have a 2+ charge. So they're soft, you can cut them easily with a blunt knife, and they have relatively low melting points, although they are certainly lithium, sodium and potassium are solids at room temperature. Now let's look at their reactions with water. So here we've got a table, and anywhere on the internet you can find videos of these reactions, and I'm just going to summarise what you actually need for the IGCSE exam. Now, with all these metals, they all float on water, which is a little bit surprising because normally metals sink in water, but these all float, and that's again because of the weak metallic bonding. Means the metal just isn't packed quite as tightly as in other metals, so they're actually less dense than water. Now, when you put lithium in water, first of all, it floats, okay, bubbles then start to come off from the lithium, it effervesces, and it tends to move around the surface, so floats and moves around the surface. Now the bubbles, you might think, well, what gas have we got? Now, if we are considering what gas, first of all you'd look at it and they're bubbles of colourless gas, and so lots of my students will say, it's a colourless gas, it's going to be carbon dioxide. And then I'll ask the students to actually consider what elements are present in the reaction, and if we've only got lithium and water, you can see that there's no way that can be carbon dioxide gas coming off. So we'd test the gas, we'd trap some of the gas in a test tube which had been filled with water, and the water sort of gets bubbled out, and we test it with a lit splint and it goes pop. So you get bubbles of hydrogen. Now it's important, if they ask in an exam what are the observations, that you don't just say hydrogen is produced, because that isn't an observation, that's not what you've seen, but you have seen bubbles, you have seen it floating, you have seen it moving around the surface, and eventually the lithium would disappear. And the reason it disappears is that it forms a soluble product. It forms lithium hydroxide, which dissolves in water. So you don't see solid lithium hydroxide appearing because it dissolves in water. So eventually the lithium will disappear. And at the end, we test the water with universal indicator, and universal indicator turns blue or purple when it's in the water at the end. And that's why group 1 metals are often known as alkali metals. Not because the metals themselves are alkali, but because when they react with water, they produce an alkaline solution. So in lithium's case, it's lithium hydroxide. Now you will need to know how these observations change for the other metals. Now, in all of them they float and moves on the surface. Okay, and actually, rather than me write these out, I will just put an arrow to show that we also get bubbles of hydrogen appearing with sodium. The sodium also disappears. The universal indicator also turns blue or purple, but with sodium something else happens, and sodium is so reactive that it melts on the surface of the water. Okay, so not only does it float, okay, but it forms a molten ball of metal. Which is spherical in shape. And I think that's always really impressive because you put any kind of shape of sodium in, like a cube, okay, and within a split second it's melted and formed this sphere that powers round on the surface of the water. And again, it forms an alkaline solution when you put it doesn't form the alkaline solution when you put the indicator in. The indicator shows you've got an alkaline solution, and that solution is a solution of sodium hydroxide. So how does this change with potassium? Well, again, potassium produces bubbles of hydrogen. Okay, the potassium does eventually disappear. If you put universal indicator in at the end, you'll get a blue or purple colour appearing, showing you that the product, potassium hydroxide, is alkaline. But one of the other things you'll see is that potassium, not only does it float, okay, and it moves on the surface, but it's an incredibly exothermic reaction with potassium. It's much more vigorous than with sodium and with lithium. And it will actually ignite. So you will see a lilac flame coming off the metal. Now, the next thing we should consider is what happens to the reactivity as we move down the periodic table from lithium to sodium to potassium. Well, first of all, it's worth noting that all are pretty reactive. If you put a lump of iron in water, it doesn't bubble vigorously. These three are reactive metals. And as you go down the periodic table, they clearly get more reactive. So this produced bubbles very quickly, this formed a molten ball, and this one caused a flame to form. So potassium is the most reactive, and that's what we're going to look at next. And this diagram hopefully helps to show you why potassium is the most reactive. These metals all react by losing their outer electron. And they lose their outer electron, so they form an ion. An ion is a charged atom with a complete outer shell. the easier it is for an atom to lose that electron, the more reactive it is. And you can see here that lithium's electron is quite close to the centre of the atom. It's quite close to the nucleus. And inside the nucleus there are protons and they attract the electrons. So lithium's protons are nice and close to that outer electron. So relatively, compared to the others, lithium holds on to that electron reasonably strongly. Sodium is a bit bigger. We've added an extra shell, and so that electron is just a step away compared to the lithium from the nucleus. Okay, the nucleus with its protons that are holding the negative electrons in. So the sodium will lose its electron more willingly than lithium. And look at potassium. Potassium's outer electron is much further away. Another shell has been added. So potassium is going to be the most reactive because it loses its electron the most easily. So how would you structure that in an exam if they asked you to explain the increase in reactivity? Well, first of all, you could say that there is an increase, or, well, let's start off by stating that in reactions, the atoms lose their outer shell. And they do that to obtain a full outer shell of electrons. That outer shell, and I probably should add their outer shell electron. It's not the shell they lose, it's the electron. Potassium loses its electron most easily as the electron is further from the nucleus than in sodium or lithium. Therefore, the attraction of the nucleus is weaker on the electron in potassium than sodium or lithium. And what you might like to consider now, or what might get asked in an exam is, they might say, talk about the reaction of potassium and describe what you'd see when you put it in water, and then they might say, well, actually, compare that with what you'd expect to see for rubidium or cesium, which are two elements that we haven't looked at, and they're below potassium in the periodic table. So they'd ask you to make a prediction, and really it's exactly the same as what's here. The electron for rubidium or cesium will be further away from the nucleus, therefore it will be lost more easily than in potassium, which makes rubidium and cesium explosive. And there are some great videos, particularly done by Periodic Videos, on those reactions.